Okay, hi everybody. So this one is an interesting problem and I find it sort of hard to explain, so I'll do my best. But I think you'll see it's not too bad. So first, here's the map. Let's call it F. And I guess the inputs are R2 and the outputs are R3. Okay, and so because there's two inputs, the Jacobian will have two columns. So I'll just write that. Jacobian has two columns. So the partial derivative with respect to the first variable, x1, is what it's called in this particular example. It gives a velocity vector, 2x1, x2, 0. Do you see how I got that? The 2x1? Do you see how I got x2? And the last one is 0. Similarly, partial x2 gives another velocity vector, 0, x1, 1. These are single variable calculus derivatives, but now we're going to put them together. So what we'll do is that basically the derivative will be a linearization of the map F. So the map F is non-linear. And so it's complicated. You know, it has squaring, it multiplies variables together. Actually, this part is linear, but it's going to be a curvy surface in R3 that we get. And so we'd rather do is choose a point and linearize at that point. I guess it's an input point. We're going to choose an input point. Let's call it P equals x1, x2. And so then create. Then what we're going to do, once we've chosen a point, create a linear map sending movement vectors, sending linear movement vectors, V, to a linear combination of Jacobian columns, So I guess maybe a quick picture. Let's say this is our input space, which is R2 in this case. And then our output space is R3 in this example, so I'll draw R3 over here. And let's just say that, so a rectangle here gets mapped by F and becomes some sort of a surface. And it's probably going to curve around in some weird way because the map F is nonlinear. Okay, the map F is nonlinear. But if we choose a point, if we actually pick a point here, like that point, or here, let me pick it in, how about a pink point. This point here, P, and then somewhere will be F of P. Maybe F of P will be here. F of P. Okay, let me get rid of this thing. Now, what we'll do is we'll linearize there. So what we'll do is create another map, a completely new map. This is the linearization of F at P. And I'll just say that in words. The linearization of F at the point P. We had to choose a point to linearize. And what it'll do is it'll send that same rectangle to not a curvy surface, but actually to some sort of a flat surface. And it'll include that same point. Okay. Roughly, this is what's happening. So, and this map will be linear map. Okay. Now, what is the linear map? Well, it's just going to be a linear combination of these things. So I guess what we could write is, we could write that v1, v2 would be like some movement vector in the input space gets sent to v1 times 2x1, x2, 0, plus v2 times 0, x1, and 1. And so this is a linear combination, so this will be a linear map, provided we have actually chosen the x1, x2 values of p. So, you know, if, yeah. So I guess if we plug in, if p equals x1, x2 is actually a specific point, like 1, 2 up here, is a specific point, then we get a linear map that says v1, v2 should go to v1 times see what I did? I just plugged in. I plugged in the values. And so the Jacobian columns now become like actual vectors. And we just take a linear combination of those actual vectors. And that's why we get some sort of flat thing. This green thing becomes flat. Because all we're doing is we're taking linear combinations of what? Well, of the derivative of these curves. So like somewhere is this curve, has that derivative, somewhere is that curve, the vertical curve, and has some other derivative. And then we just take linear combinations, which will give us this flat thing. So anyway, and then like if we actually choose a direction, so if we choose a movement direction as well, if we move in direction v equals, let's say, -1, 3. I'm just choosing an example here because that's what the problem said. Well, compute it in that specific direction. Then now we actually just plug in. We plug in and we get a very specific linear combination, namely -1 times 2, 2, 0 plus 3 times 0, 1, 1. So see, I just plugged in. And so what's this? -2, 0. And what's this one? 0, 3, 3. And so now I just add the vectors, and I get -2, 1, 3. So you see that it's sort of, we keep plugging in more things. So at first, if you just take the Jacobian columns, if you take those two velocity vectors, movement in the first and second dimensions, you'll see that you have variables remaining. Most often, there will be variables x1, x2 remaining. Now, that means that we haven't chosen a point. We haven't picked a point to linearize, because if you linearize at a different point, like let's say I linearize at this point right here, maybe that's over here on the surface as f of that point. If this was, maybe we can call it q, then this would be f of q right there. And then that same rectangle would get mapped to a completely different plane. Right, so if you linearize at a different point, you're going to get a different linear map because you're going to plug in different numbers, and so you're going to take linear combinations of different vectors. And anyway, this is the geometry that's happening here, is if you linearize at different points at the input space, then you'll apply that map and you'll get different planes. These will be tangent planes to our curvy surface, and they will be tangent at different points, either f of p or f of q, depending on if you linearized at P or if you linearized at Q. I guess this one would be linearizing, taking the derivative of f at the point Q would be this red, well, that's sort of represented in our picture as that red plane. Okay. So now, how can I describe this? Well, let's look at what the question is saying. Compute the derivative at an arbitrary point. So here is the derivative at an arbitrary point. I'll label that as my answer to part A. Compute the derivative of the map right there, a specific map, at an arbitrary point. Arbitrary point means I did not actually plug in values for the input points yet. Okay. And so this is really, like, when I look at this, it's not yet a linear map because here, like, v1 and x1 are multiplied together. v1 and x2 are going to be multiplied together, and that's not linear. It's like degree 2 quadratic. And so really this is like a family of many linear maps because we didn't choose a point to linearize at, because we didn't choose where to linearize. In other words, the original input variables, in this case x1, x2, are still there. They haven't been plugged in with numbers. Okay, that's here. Okay. Now, so it's sort of like a nonlinear family of linear maps. That's what it is. Now, what about linear maps and numbers? So in B, let's see, compute the derivative at the point x equals 1, 2. So now we've actually chosen 1 and 2, or 1, 2 as the point where we're linearizing. So that's down here where we plugged in. You know, all these x1, x2s became numbers. And we haven't yet picked v, so at this point, this is part B, and here we chose a point, chose a point to linearize at, namely x1, x2 was 1, 2. And so we get, so right here, like this formula right here, that is a map. It's what we usually call it the derivative of f at the point P, and where we've chosen P. So that's a linear map. DFP is a linear map. So compare that to part A up here. This is not quite a linear map yet. It's a whole family of linear maps, depending on when we finally choose x1 and x2. You know, this is many, many linear maps, depending on where we linearize at. Okay. Now finally, when we also plug in for v, now here, this is part C, now we also plug in the linear movement, v equals -1, 3 was this example. So our linear map is evaluated at that point, at v equals -1, 3, giving a vector. So here we had a linear map, here we had a vector, and here we had a many linear maps, or a family of many linear maps. I hope this makes sense. If not, that's okay, because this is the first time you're seeing it, and it takes a while. So I guess let me summarize. If we have, so this is now a complete answer. I have answered all the parts, A, B, C, D, of this question. Let's just double check that. Compute the derivative at an arbitrary point. Yes, right here. And then I've also stated that this is really a family of many linear maps, just waiting to become a linear map when we plug in for the x's. Then we get just a linear combination. The v's go to a linear combination. That's a linear map. Okay, and then compute the derivative at this point. So now we've picked the point. Now we'll finally get an actual linear map. So this will be a linear map here. Linear map. The answer of part B will be a linear map. The answer of part A was many linear maps. We didn't choose which one yet. And then the answer of part B is actually we plugged into the linear map and we got a vector. Or sorry, the answer to part C, compute the derivative at the point x, we've chosen that, and the direction v. And so we plug in the vector v to our linear map, and we get an output, which is now a vector. And so I guess one thing I want to point out is that if your original map is from R2 to R3, then the derivative at a point will again be a map from R2 to R3. The same input space, same output space, except we usually, we usually invent new variable names, v, for a movement vector, a linear movement. And this will go to a linear combination because this is a linear map. Linear map. This original map will most likely be nonlinear, and its formula won't just be a linear combination. Its formula will be more tricky, like x1 squared, x2 minus 3x2 to the fifth, comma, x1 squared minus 2, comma, x2, which I guess I could have written as x2 to the third. Anyway, all these are nonlinear, and so they're more complicated than just a linear combination. And here we usually have input variable names that are different, because these are different maps. And basically this one is sort of hard, and then so we linearize at a point to make it easier. Okay, but it's just a version of the same map, so it'll have the same input space and the same output space dimensions, and sort of visually the nonlinear map has this curvy surface as its image, whereas the linear maps will be these flat surfaces. And of course there's many of them depending where we linearize. Okay. Practice this one on your own. I guess let's look at my other solution. Here is my other solution. Nonlinear map. And then the linear map should just have a formula which is just a linear combination. So that's what we see here. And then I said in words, since we have not chosen a specific point to linearize at that point, this expression represents many different linear maps all at once. To get a linear map, to get a specific linear map, we need to choose values for x1 and x2. These need to become actual vectors. And then the variables are going to be these coefficients. Okay, so if we do that, we actually choose the point. These become vectors, and now we get honest-to-goodness linear map, sending these coefficients to a linear combination of those vectors. Choosing an actual direction, we plug in, and we get an output, namely this linear combination, which is now actually a vector. And, oh, actually, this is a good notation. See, this is the notation for plugging in an input value. And since df sub p is a map that has inputs, again, R2, and outputs, again, R3, we plug in some v, some vector, and we get out another vector out here.